Okay, then shall we start? Okay, so let me review what we did in the previous class. So in the last class, we looked at basically one example, and that is the example of a slow flow in a wedge-shaped hopper. So we did an example related to statics. Now we're looking at slow flows. Again, these flows have the characteristic is that they are determined entirely by friction between particles. So we looked at the governing equations. These are the continuity equation and the momentum balance equation. And we saw that for 3D problems, you have 4 equations and 10 unknowns. Density, 3 velocity components, 6 stress components. And for a 2D problem, you have 3 equations, which is the continuity and 2 components of the momentum balance, and then you have 6 unknowns, which is density, 2 components of the velocity, and 3 components of the stress. So obviously we need some more equations, and they come through the constitutive relations. These relations, they determine the property of the material. These are just general equations. They say that, okay, mass is conserved and momentum is conserved. But you need some information about how the material behaves, and that comes in these constitutive relations. And the first approach that we took is this Mohr-Coulomb approach, in which the density is constant and then there's incipient failure at all points. Next time we'll look at, today we'll look a little bit more at this critical state approach. Okay. And the main difference between this and this is here the density is allowed to vary, whereas over here density is constant. So this is the problem that we spent all our time on last time. And this is 2 plates. So we are looking at it from side on. So you have one plate here and another plate here. And there in between there is granular material. And what we assume is, of course, that the density in here is a constant. That the gravity acts in the radial direction. That means at any point, if you draw a gravity vector, it will be pointing towards the origin. So we are using cylindrical coordinates where r is the radial distance and theta is the angle from the vertical axis. Another condition that we assume is that the walls are frictionless, so mu w is 0. And we also assume incipient failure everywhere, so the Mohr-Coulomb condition is satisfied at all points. And because of these two things, you have shear stress is 0. And once shear stress is 0, that means the other 2 components, the normal stresses, are principal normal stresses. And since you had incipient failure, the ratio of these 2 is a constant, and that is K. So then we saw that with these assumptions, the continuity equation just becomes this. And that gives us a solution that the velocity goes as some constant divided by r. And the momentum balance reduces to this. And then if we substitute for sigma theta using this and VR using this, then we get a very simple equation which can be solved, and applying the boundary conditions like this, we can get the constant A, and from that we can get the velocity as just given by this. And what is the nice result here is that this velocity is independent of the height of material in the bin. once the height becomes large enough. So it just is G times R1. So it depends only on the size of the orifice. R1 is the orifice size, and this is the coefficient of, this depends on the angle of internal friction. So this is a very nice and simple theory. And as I was saying last time, we can easily do simulations to check this. And so one of the students in the lab, Afroz Momin, she's doing her PhD on this topic of flow in a wedge-shaped hopper. And she has done simulations which are exactly according to the assumptions of the model that we just saw, that you have frictional inelastic particles, but the walls are frictionless, and you have radial gravity. So it's very easy to do these things in simulations, but not so easy in experiments. The hopper is filled. So how do we do these simulations? First, you fill the hopper. So maybe fill the whole thing. These are walls, so you can't fill in this region, but you can fill right up to the top here. So just pour the particles in and fill it. So you can't make out, because these are very large number of particles. There are 130,000 particles here, and so they look like a sort of continuous system almost, but they're tiny dots you can make out. So you fill it all up to here. Then you remove all particles which are above r equal to r1. So you get this nice round surface on top. Then we open the exit from here, and then the flow starts. So it starts from 0, then slowly it reaches steady state. And once it reaches steady state, then we start collecting data for a short time. So let's say as you open it, this height will start falling. And we collect the data for a very short time so that the change in height is small. So in fact, in most of the simulations, only 3,000 particles are allowed to go out, during which we collect the data, and the height falls by, let's say if this is 15, then the height falls by 0.2, 0.3. So it's very small distance. So these are the results. This is the velocity, Vr, divided by square root of G. Over here, B is the same as R1. And you can see that the dots are what you get from the lamp simulation, and the line is what is the theory that we just discussed. And you can see that there is a really nice agreement between the two. But one of the things that we do over here is that we actually fit this line to get the constant A. And that A is given by here, by this. The next one, we calculate the stresses. You know that in lamps, it's easy to calculate stresses. So from the simulations, though I'm not showing it to you, we do find that sigma r theta is almost equal to 0. That is, as we have assumed. So even the simulation results give us the same thing. So you do indeed get that sigma rr and sigma theta theta are constant, are principal stresses. And then if you plot the two normal stresses divided by rho GB, so this is a sort of dimensionless quantity. If you plot that versus the radius, like the expression we had got in the class, then you can see that you get this type of behavior, that the stress is 0 over here, but it doesn't, the exit is over here. At some point here, the exit is not at 0, but at some point over here, maybe here, sorry, this is the exit. And you can see that the sigma rr and sigma theta theta don't go to 0 at the exit. So when we want to compare the theory to this, we cannot use the second boundary condition that sigma rr is equal to 0 at R equal to R1. So instead, we use the fitted value of A in the theory rather than using the boundary condition. And if we do that, then you see that the agreement between the simulations and the theory is really quite excellent. So this is the full theory, and this is the theory if we assume A is equal to 0. And you can see that really the inertial term that we have on the left hand side, if you remember this term. So this is the inertial term. So even if we put this term equal to 0, you get almost exactly the same match. That means that the inertia has no effect in our system, mainly because this is a small system, and the velocities are quite small. If we go for an industrial scale system in which, instead of 130,000 particles, there are billions of particles, and instead of 15 centimeters, the height of the hopper is 15 meters, then of course the inertial term could become important in that case. There is one more unknown in the problem, and that is K. And we use that also as a fitting parameter. So since we are not applying a boundary condition, so we need one more way of finding out this K, and we use this as a fitting parameter, and we find that this is about 2.27. So K is this. And you can see that the agreement with both sigma RR, which are the blue dots, and sigma theta theta is quite good for this value of K. And you notice that here we have plotted sigma RR and we have plotted sigma theta theta, because we know sigma theta theta by sigma RR is K. So both these should actually be exactly equal. There are slight differences, but they are nearly equal to each other. So this shows that the theory is quite good. And in fact, now if we go back to our previous what we were doing, which is the case of no flow. So supposing we wanted to calculate what is the stress distribution in the system when there is no flow, that is velocity is 0. We can do it for the same system, and you see again the agreement between theory and the simulation results is extremely good. But here now for the static system, you get a smaller value of K. And so, this is the main difference, that the theory is the same. The only thing is the effective friction angle becomes much lower over here. Another thing that I wanted to tell you is that K is always greater than 1. And so what does that mean? When you look at this, if K is greater than 1, that means sigma theta theta is always larger than sigma RR. So sigma RR is the normal stress in the radial direction. Sigma theta theta is the normal stress in the theta direction. So this stress is always smaller than this stress. That is because the walls are in some sense compressing the fluid. So this stress becomes the major principal stress, and this is the minor one. So here, you have zero stress here and nearly zero stress at the exit. So that's why there is a, what you can say, a lower stress in this direction. And because there are solid walls over here and because of the flow, there is essentially a compression that's going on in the theta direction. So you actually have a higher stress in the theta direction. The final thing I'd like to show you is that, if you actually just from the simulations, if you calculate the value of K, then you can see that it's nearly constant, but there is some variation. So this is 2.27, and this is the fitted value that we got over here, 1.35. Those are the dashed lines. But the actual data is slightly off. And that's the reason for, the slight deviations that you are getting. So, why, this happens is because, of course, the local packing, everything varies. So you can get slight variations in the friction coefficient because of that. And then one of the assumptions of the theory is that density is constant. Well, this is a plot of the solid volume fraction versus the radius for both the flowing system as well as for the static system. And you can see that for the flowing system, there is a variation. Of course, remember, this is going only from 0.58 to 64. So this variation is small, but there is a small variation in the density in the flowing system. In the static system, most of the density is constant. And over here, of course, this is because of the filling, because we fill from the top. So that's why there's a little bit of compaction at the top. But if you look at this part, here you can clearly see there is a change in density for the flowing system, and this is nearly constant. Okay. So these are some results which tell you that, in fact, this theory that I'm telling you about is quite nice, and it can be used very well to describe these, both the static flow as well as, the static system as well as for the flowing system. Okay. But the reason I showed this last graph is to tell you that really, if you are really want to be very accurate, then you must take this density change into account. And how do you take it into account? Our Moore Coulomb theory cannot give us what this density change will be. So we have to go to some other theory, and that's what we want to discuss today, and that is the critical state theory. Okay. So any questions? So if there are no more questions, then let me continue. So today I want to basically just discuss, some aspects of critical state theory. And when I stopped last time, we were here, we had just derived this. And so we go on to the next lecture. So we will now come to a new topic. Today is lecture 19. And we are in September 7, 21. Okay. And I want to talk a little bit about this critical state theory. So this is a theory for slow flows in which the variation of density and so forth, and how the yield criterion depends on the local density, and all these things are taken into account. Okay. And so we can just write that down. Okay. And Reynolds, has anyone heard this name before, Reynolds? Someone is supposed to answer.
Sir,
Yes.
the Reynolds number.
Yeah. Do you know his first name? What is Reynolds' first name? Okay, so his name is Osborne Reynolds. Okay, so he's one of the great fluid dynamics researchers, and as it was mentioned, he essentially established this transition to turbulence and so forth, which is so important. Uh, but he also discovered, when he was playing around with granular materials, he also discovered that granular materials.
Hello, sir. Sorry. Hello.
Hello.
Sir, sorry to interrupt. You are writing in a pad now, so that is not showing. But I
Oh,
don't
okay,
know.
okay.
Critical state theory is showing.
Yeah, yeah. Thank you. I will start sharing the right thing. But yeah, I'm sharing the wrong. Now, okay.
Yes, sir. Yes.
Thank you. Okay, so this is what I had written down. So he essentially found out that granular materials dilate when they are deformed. So if you try and deform, and this is an experiment that people can do. So, for example, supposing you take a bottle, plastic bottle, okay, and you put a straw in it, and let's suppose this is filled with sand or mud or whatever. So if you press this, then what actually happens is that this material dilates and this level actually falls. That there is more space available for in the sand, and hence so the actual effective volume decreases because of the dilatancy of the sand. And so this is the basic idea that the reason is that if any granular material, let's say it's in a packed bed form, and if you try and deform it, you can imagine that the particles have to first move apart before they can actually go from one place to the other. Because if they're all stuck together, then it's impossible for them to move. So, you can do these. Another experiment that can be done is that if you put, let's say, any granular material in a plastic bag and then apply a vacuum on it, then it becomes completely rigid. And the reason is that the material cannot dilate and hence it cannot move, and so it behaves just like a solid. It cannot deform, so it just behaves like a solid. So really this is the key aspect, that slow flows are accompanied by tiny changes in density. And in fact, what actually happens is that if you apply a stress on a granular bed, so the stress can lead to either not, it's not always that it will dilate, it can sometimes compact or it can dilate depending on the initial state. Okay, so if it is loosely packed and you apply a stress, then it will compact. If it is already very densely packed and then you apply a stress, so this stress, of course, leading to deformation. So if you put enough stress to deform the granular bed, then it may compact or dilate. And there were many studies done which showed that the material will tend to a particular state known as the critical state by either compacting or dilating. So and then it becomes essentially constant. So upon deformation, it will just go towards the critical state. So that means it will either become more dense or it will become less dense, depending on the stress that is applied and on its initial packing. But then after you wait for a long enough time, the system will just slowly approach this critical state in which there is an equilibrium between stress and density. So that means the density will reach a certain state depending on the stress and so forth. And that state is called the critical state. And so what we'll see now is that in fact we will show that at the critical state, the Moore Coulomb criterion is that. So what we can say is that the critical state theory is a generalization of the Moore Coulomb theory. And if you start from a system which is not at equilibrium and then you apply a stress, then the density of that system will slowly change and it will approach the critical state. And at that critical state, Moore Coulomb will apply. So let us see how this happens. And we'll do a simple analysis of the approach to so let's say your system starts at some point. Are we guaranteed that it will always approach the critical state? So I'm going to make a drawing here, and this is a drawing of, if you remember, the yield function in the case of the critical state theory is just given as f of sigma 1. I'm looking at a 2D system, so sigma 1, sigma 2 and density is equal to 0. So if we keep density constant, then we will get a curve. So let us, if we plot now here, this axis is sigma 2, that is one principal normal stress. This is another principal normal stress. This 45-degree line essentially is the line along which both the stresses are equal. So if you are in this part of the plane, then sigma 1 is equal to sigma max and sigma 2 is sigma min. And over here you'll have a symmetric thing. So here sigma 2 is equal to sigma max, and so really everything that happens on one side is exactly symmetric to the other side. Now this yield function, when density is constant, is going to be something, it will look something like this. And of course, due to symmetry, it will be also like this. Okay. So let's say this is rho b is equal to rho b1. And this is for f. This line corresponds to f equal to 0, but with rho b equal to rho b1. So those two conditions are there. So f is equal to 0 and rho b is a constant. This gives us that sigma 1 will be some function of sigma 2. And so this is how the yield line varies. So it's not a straight line, it's a curved line, and it increases slowly and then it starts to increase faster until this point, and the line ends over there. And let's define this line D. This is a unit vector along the diagonal as D, and let's define a normal vector to the yield curve to be n. Now we want to find out that which is the yield point, which is the critical point on this curve. So the basic idea of this critical state is that at that point, the sigma 2 and sigma 1 are such that there will be no change in the density. So del rho by del t will be 0. Okay. So first let's start with this. So since this line is f equal to 0, so we can say something about the slope and we can find out the equation of the normal and so forth. So first step will be to I want to find out the slope of this line. So at any point, what is d sigma 2 by d sigma 1? That's the first thing I want to do, given that f is equal to this. So if I write down the total differential, then df is just del f by del sigma 1 d sigma 1 plus del f by del sigma 2 times d sigma 2. And of course, in general, there will be also the density term, but we are only interested in a constant density. Rho b is equal to rho b1. So these are the only two terms. And so on this line, this must be equal to 0. And if this is the case, then we immediately get the slope of the line d sigma 2 by d sigma 1. This is the slope of the yield curve, constant density yield curve. This is from this equation, if you rearrange, you will just get this is just del f by del sigma 1 divided by del f by del sigma 2. So that is what is the slope. For the constant density. Now, if you look at this normal vector, then, I want to relate the components of the normal vector to this slope. So you can just see that the slope of the normal vector So, if you write down this, the two components are like this. So N1 and N2, I'm sorry, the two components of the unit vector are here. One is in the direction of sigma 1 and 2 is in the direction of sigma 2. So you can see that the slope is just equal to N2 by N1. So the slope of the normal vector is just N2 by N1. And so this actually gives us that this multiplied by d sigma 2 by d sigma 1, since the normal vector is orthogonal to this, the product of the slopes should be equal to -1. Okay. So this means that n1 by n2 is equal to minus d of sigma 2 by d sigma 1, which in turn is just equal to del f by del sigma 1. Okay. So I've not really done anything I've not done any physics over here. This is just pure algebra. That is, given any curve like this and n being any normal to that curve, then the components of the normal are related to the partial derivatives by this simple formula. Now, so this is one result. Okay, now, if you remember, so this was one part of the critical state theory, that you have a yield function, and let's suppose you have the second thing, and that is the flow rule. That is the second part of the critical state theory, the flow rule, which basically states that d1, which is the principal component of the rate of deformation tensor, is equal to lambda times del f by del sigma 1. So this is for an associated flow rule. And del d2 is just lambda. So this essentially gives us a relationship between the rate of deformation tensor and the stresses. So if we eliminate these, I mean, if we eliminate lambda between these two, then you can clearly see. So this, I'm saying, is the second component of the critical state theory, which is the flow rule. So the first one is the yield function, the second one is the flow rule, and the third will be the coaxiality condition, which we may or may not need. But if we want to calculate the rate of change of density, then we have to know something about the deformation, and this equation will relate how the deformation occurs as we at different points along this curve. So now you can clearly see that I can relate d1 by d2 to the ratio of those two, and so I have okay, so this eliminates lambda, and this essentially tells us that the components of the normal vector n1 and n2 are directly related to the principal components d1 and d2. So this is another important result. So the rate of deformation components are directly related to the components of the normal vector. Now, let me just go a little further ahead and the third thing I want to talk to you about is the continuity equation. Because we want to know what is the rate of change of the density. So I should know the density is actually related to the velocity through the continuity equation. What is the continuity equation? Well, if we write it in the Lagrangian form, so this is the material derivative, which is of course del rho v by del t plus v dot gradient of rho v. So this is the material derivative. So it just basically says that for a given fixed material, how does the density change? So if you take a small volume within the fluid and then you want to see rate of change of density, this will give you that. A small volume of particles. And this is just equal to minus rho v divergence of v. So this is the equation we want to use, that the rate of change of density is just minus rho v times divergence of v. Now, one of the things that we can write down is that divergence of v is just equal to trace of d. So this is an identity and I'll show you that it's true. So now we can relate divergence of v to the rate of deformation tensor. So you can see where I'm going, that eventually I'll be able to relate the rate of change of density to the components of the normal vector. Just wait a little bit. Now, why is this an identity? So what is trace of d? Well, this is nothing but trace of half of the trace of gradient of v plus gradient of v transpose, which is equal to half of the trace of gradient of v plus half trace of gradient of v transpose. Now, trace is nothing but the sum of the diagonal elements. So transpose makes no difference. And we also know that trace is nothing but the sum of the diagonal elements, which is nothing but divergence of v. So this is equal to divergence, half divergence of v plus half divergence of v, which is just divergence. So this is the proof of the identity. So this is what we want to go with. So we then can find out from the continuity equation that the rate of change of density of any element is just minus rho v times trace of v. Now, trace of any tensor is an invariant, and so this we can essentially write for any coordinate system, trace of d will be the same, and this is nothing but equal to minus rho v into the principal components. Because remember, when you do a principal, when you get the principal components of the tensor, they are basically the diagonal elements. So when you take trace of that, it's just the sum. So this is what is the trace. So you can see that this is nothing but minus 1 by rho b d rho b by dt is equal to d1 plus d2. Okay, so I hope any questions now? Okay. And the final thing that I want to tell you about. So we have seen that if we can get some expression for d1 plus d2, well, we can relate it to n1 and n2. But now n1 and n2 is here. But what I'd like to do is I'd like to take the product of, now I come to the unit vector d. We have unit vector d is along the diagonal, so this is nothing but 1 by root 2 of e1 plus e2. So this is the unit vector along the diagonal, and if we take a dot product between n and d, then this simply gives us 1 by root 2 of n1 plus n2. So this is what it is. And physically, what is this? This is the projection of the unit normal okay. So here, if we see this, the dot product between this vector and dot product between this vector and this vector will give us a line on this, which is nothing but the projection of this line on this line. And that is just equal to n1 plus n2. So now you can see where I'm going, because I already know d1 and d2 as divided as n1 plus n2. So if we write down, let's say, substitute for n2 as just equal to from the earlier one. So if I write down n2 is just equal to n1 into d2 by d1, correct? Through that one. So then this gives us the projection is just equal to 1 by square root of 2 into n1 plus n1 into d2 by d1. So now if I take out n1 divided by d1 common, then you see that this projection is just equal to 1 by square root of 2 n1 by d1 plus d1 plus d. So this, by doing little bit of algebra and so forth, you can see that this projection n dot d is just equal to, is directly related. Now if I substitute for d1 plus d2 from this equation, then you can see that this is nothing but minus 1 by root 2 n1 divided by rho b d1 into d rho b by dt. So in a very general sense, what I have shown you is that this projection that is the projection of n onto D, is directly related to the change in density of the system. So here, what we want to know is that at what point do we reach the critical state? Now, the critical state we must have the condition that the rate of change of density must be equal to 0. Okay. So what does that mean? That means we come to a geometrical condition that n dot d is equal to 0. So what is n dot d? When is n dot d 0? Well, if we go back over here, the only time that n dot d will be 0 is if n is orthogonal to d. So that means when you are over here. So this essentially will be the critical state when n is orthogonal to d and the projection of n onto d will be 0. So this is how you would get the critical state. And so for any such curve, so it doesn't matter what that curve is. If you look at this, over here, the rate of change of density will be negative, so it will go outward. I'm sorry, it will go inward and then come to some other critical state. Over here, the rate of change of density will be positive, so then again it will shift to some other density curve. But over here, if you are exactly at this point, then this will be the critical state. So the way that the physical system goes is that it will jump. There will be many nested curves like this. So I'll just draw one or two more. So this at a different density, you may have a curve here, or you may have a curve here, and so forth. So there'll be many such curves, and for each one, we can get the critical state. So for a given stress condition, if you are not at the critical state, then the system will keep on deforming and the density will keep on changing until you reach a critical state. And so this is really the general sort of analysis, because we have done it for any arbitrary yield function. We show that for the condition of criticality, we must have n dot d equal to 0, and that essentially means that your it's directly related to the yield function. So your n1 plus n2 is 0, and that tells us something about the slopes of these curves also. So we'll do exactly the same example that we did for the Mohr Coulomb, that is the wedge-shaped copper. We'll see how this particular theory, it seems a little complicated now, but it's actually quite simple. How this theory can be applied to the and what we will find and what will turn out is that if you look at all these curves, let's say you have many different curves, then in all of these cases, the critical state, I've not drawn it properly, but this is the Moore Coulomb criterion, and these are the critical states. So the locus of the critical states satisfies the Moore Coulomb yield criteria. I didn't show that. That will, so that means we have to choose our yield function f in such a way that this always happens, and we'll see in the example how that is done. So every critical state is actually the Moore Coulomb state. So when we look at the Moore Coulomb yield criterion, it's satisfied for any ratio of sigma 1 to sigma 2. We say sigma 1 divided by sigma 2 is equal to k, but that value of k will change as let's say that value of k is constant, but the density of the system will change at different values of sigma 2, and that is not predicted by the Moore Coulomb criterion. However, it is predicted by the critical state theory, because this will be at some rho b1, this will be at some rho b2, and so forth. So as sigma 1, sigma 2 change, your density will also change. Okay, so with that, I'm sorry, I should have shown you this. I'm writing something and I didn't show it. So the last thing I was talking about is that if you plot different of curves and then you plot the critical point on each curve, then the locus of the critical points lies along the Moore Coulomb yield criterion line. And so the basic point is that these two theories are not contradictory, but the critical state theory reduces to the Moore Coulomb theory if you are operating only at the critical state. Okay. So I'll stop with that. And so today you have to submit your homework assignment.